All right, today was day 84, and we had an interesting day, so not everyone was able to attend. Question for today was, can we recycle our way out of climate change? Yesterday, we introduced our renewable energy unit, and one of the things that lots of students mentioned as a solution for reducing or controlling global climate and temperatures was wasting less and reusing and recycling more. So, for today, we're going to look and see what's recyclable and what's not, and then look at the viability of recycling as a method to reduce energy usage and climate change. For your warm up, the question was simply, can we reduce, reuse, or recycle enough to solve all of the temperature and climate change problems? So that's basically a yes or no thing. And then a little game about recycling and what can be recycled and what can't. We talked about this table here to see what goes in each of your bins, and specifically to look at some areas that have questions, like plastics. So we talked about how there are only certain plastics that can be recycled, 1, 2, and 5, and that things that have films on them, like plastic bags, but also like the water bottles that lots of students like to use, have to be taken apart to some degree in order to actually recycle them. So we discussed some of that stuff, and that other mixed media things like rubber hoses, even though there might be something that feels like plastic there, that you can't recycle that. So we discussed those things, and then moved on to look at some sections of our climate change activity intro. So let's see, where are we? Here we go. So with carbon and climate, the discussion here was about the article that I gave on yesterday, and why don't climate scientists agree when it comes to global climate change? This is something that that some skeptics point to as a reason to say that climate change isn't real. And so we discussed this paragraph here about there being less agreement in the scientific community about climate models. And one of the things that we pointed out was that all of the models that look at like what would happen temperature-wise if you did this, if you doubled the amount of CO2 in the atmosphere from pre-industrial revolution levels, that they all show that temperatures would rise. All right, the most conservative models show a rise of a few degrees Fahrenheit, and the most aggressive ones a rise of almost 10, with others in between. So the disagreement isn't, and this is the important part, isn't that like some folks think that, oh, I guess here, put it this way, the question that I asked was, what disagreement would show up if these models maybe didn't have much validity? And the answer that lots of students gave was that some of the models would have shown a decrease in temperature with an increase in CO2, and others would have shown an increase. And that result would mean that maybe there's something to question about these results. However, that's not what we see. All of these show an increase. So even though there's not a full agreement or an exact agreement, they all do show an increase as a result of CO2. We then talked about how the greenhouse effect works. And another point that people tend to bring up, and that is that they will ask, well, if the energy gets from the sun to the earth through our atmosphere, going down through the atmosphere, then when it gets reflected back off of the earth's surface, shouldn't it also go through the earth's atmosphere? So shouldn't there be like a net zero effect? And the answer to that is that what hits us isn't what gets emitted. It doesn't just reflect off. So if you think about going outside into the sun, your body is going to absorb energy from what? The sun's radiation, right? So, and that radiation comes in what forms? If you've looked at a electromagnetic wave spectrum, and many of you have, things go all the way from big, huge radio waves to microwaves, to infrared, to visible light, to ultraviolet, to what else is there? Oh, I guess microwaves would have been next. To gamma radiation. Like there's all these different sizes of waves, And many of them make it through the atmosphere on the way here, and when they hit the Earth or anything else, they give it energy. And then once things have energy, what do they like to do with the energy? Anything that has energy is going to try to get rid of it. And so when they get rid of it, often that getting rid of it happens in the infrared wave band. And so when that gets radiated, it's at a certain set of wavelengths, and those wavelengths get blocked by certain molecules in the atmosphere, particularly, as we can see right here, CO2. So CO2 is great at blocking infrared radiation. Some other heavy hitters, O3, that's ozone, and I believe this is methane, the CH4. So that's why those are the greenhouse gases, because they're the ones that trap that radiation and send it back in. And basically, the more of that stuff you have, the more of that blanket effect you get. So that's what we discussed there. Let's see. And that helps to answer this question number 3. And then we looked at carbon over time and looked at a graph. So questions here were, according to the graphs, what's the highest concentration in parts per million of CO2 in our atmosphere in the last 400,000 years? And when did it happen? And if you ignore the modern data, when is the highest concentration? So basically, when we weren't messing with the atmosphere because we didn't have industry, when was the natural high versus where's our kind of unnatural modified high? One little note, parts per million, so I'll open this up. Parts per million means that if you took a sample of air, maybe you grabbed a sample of air in a bag, and then you analyzed what was in there, and there were 1 million molecules, that here you'd have 320 of those molecules be CO2, and the other 999,000, what would that be, like 680 would be something else. Lots of nitrogen, lots of oxygen, lots of water vapor, some argon, all the other things that are in our atmosphere. Okay, so if you look here, this goes from this year, 1955, up to current times. And we can see these little wiggles show seasons. So high concentration and low concentration represents summer and winter. And so you notice that there's 5 of these little cycles for every 5 years. And we can see that there's a climb here. And the question I asked is this really steep? And it's kind of hard to tell. But if we use the buttons down here, let's see, there we go. We can get a bigger time range going back to the Industrial Revolution. And note that all of these yellow ones are coming from here, Antarctica, because we're using core samples to look back into the past. All this red stuff is coming from when we had the technology in the 60s through today to measure this live. So these are live measurements, the red stuff, and the yellow is measurements that we did now, but we got by digging down and looking at the past. Kind of like looking inside tree rings or something like that. Okay, so we can see a bit of a growth during the Industrial Revolution. Oops, wrong way. Before the Industrial Revolution, all right, humans definitely existed. All right, 1,000 years ago, and this is very flat. Okay, is this green stuff flat? Now we're looking back 10,000 years. And the answer would be no, it's not. Right? It is rising. Is it rising like the red part and the yellow part? No, we can see that this is pretty sharp in comparison to this. Let's keep going back. 50,000 years. Is this rising? Here on the left, no. But the last 15,000 years, yes, a natural rise. What does that mean? I don't know. Here's a bit of a decline, 100,000 years ago to 20,000 years ago, and then a rise, and aha! Do you see the pattern? I hope you do. This is an ice age down here, and so is this, and so is this, and so is this. This is 1, 2, 3, 4 natural cycles, each one something like 80,000 years long, of going from a period of high concentration of carbon dioxide and warmer temperatures down to low concentrations and cooler temperatures. And we can see that pattern was peaking right around our era right now, and then we figured things out and adjusted it quite a bit. So the old natural high was here, right, about 325,000 years ago at 300 parts per million. Our current high is around 425 or so, and probably a little bit higher since this data is a little bit old, about a year and a half old. So that was the deal there. The rest of the questions in here are, things that you could kind of wonder about and figure out on your own. Like, what would happen if, right? If we had greater temperatures, ice melts, and like which of these things might happen. Okay, last thing we did, right? So this was our little discussion about that. Last thing we did was to look specifically at recycling and see if recycling everything would get us out of climate change. And so, in order to do this, we have to think about, like, well, first, where do we get the energy that we use to make stuff? Where do we get that from? And then, like, what areas actually use that energy? So we looked here at a U.S. government site that's been around for a few years and has stayed pretty consistent with its information. And we looked at this table. Where do we get our energy from? Mostly fossil fuels, petroleum, then natural gas and coal, a little bit from nuclear power, and then a little bit from a variety of renewable energy sectors. And take note that renewable energy is 9%. This is from about 2.5 years ago, but 9%. And of that 9%, 11% of that is solar. So that means solar is 1%, wind is 2%, hydroelectric is also 1%. Relatively small things, even though we make a pretty big deal out of them. And what sectors used energy? Well, electric power generation, like electricity generation at power plants, used lots of energy. This totals up to 94 quadrillion BTUs, which are units of energy. And so 94 is pretty close to 100. And that means that about 33% of our energy that we collected up here got used for electricity, and about 29% got used for transporting things and people, and about 23 or 24% got used to manufacture things in industry, and about 7% got used for our homes to heat them, cool them, and light them, and about 5% got used for stores like Sephora or Ralph's to keep the refrigerators on, to keep the lights on, to keep the air conditioners on, that kind of stuff. So out of these, where can we make the biggest change? Like if you and I turn our thermostats down a couple of degrees or up a couple of degrees in the summer, is that going to make a big difference? Well, since we're a small piece of the pie, the answer is no. So where do we make a big difference? And the answer is over here, right? Either making this electricity with more friendly things, which we're starting to do, or figuring out how to do transportation in a better way, or not have to transport as much, and then figuring out how to do industrial and manufacturing things in a better way. And that's where recycling would really hit, and reusing. If you don't have to mine things as much, if you don't have to get new materials quite so often, then you can use less energy. There's a bit of a downside in that when you recycle things, you can't just instantly reuse them. You have to use energy to collect them and clean them and process them and turn them into new things. So, but the idea is that we can reduce this. So could we reduce it enough by recycling? Well, one of the things that this video looks at is that question. And does it make sense to do... All right, whoops. Does it make sense to do every little thing that we can do in terms of recycling in order to fix climate change and reduce global temperatures? And well, you'll see an answer, right? But think about like what you can do as a person and what your family can do, and like what we could do as a school. And then think about like, would that be enough to make a significant difference? One thing I'll give you to think about as we end is if your parents or grandparents lived in the LA area, before you were born, they might remember a time when there was a lot of smog. And for you all, there's not a whole lot of smog. And like, why did that happen? Well, that was government regulations related to pollution and emissions and fuel economy and all kinds of stuff related to cars, mostly trucks, factories, manufacturing, all those things that happen here in LA on a huge scale have to happen and had to happen in a cleaner fashion, and that was regulated. So it wasn't like, your choice or my choice. It was a top down, this is how it's going to be, otherwise it's not going to happen. And think about the air quality now. It's really pretty good, like significantly better than it was before, which is pretty amazing. So changes can happen. All right. We also mentioned that we've mostly fixed the ozone layer by changing refrigerants and air conditioners and removing chlorofluorocarbons from spray paints and hairspray and all this other stuff. So change can happen, right? But the change, you want to think about where it's most effective to point that, to have that change occur, and who needs to initiate it. I'll leave you with that.